Follow me, Hsueh-Wei. Go ahead.
Yes, thanks for your introductions. And hello, everyone. Welcome to my presentations. So at the beginning of the presentations, I briefly introduce myself. I'm Hsueh-Wei Chen, a student in Intelligence, Robotics, and Automation Lab in National Taiwan University. It's my honor to have an opportunity to share our lab research with you. So today, I would like to present to you our topics, a novel regional fusion network for 3D object detections based on RGB image and point clouds. And our supervisor is Professor Li-Chen. So, and this is the agenda today. Firstly, I will explain the background of this research and the objective we want to achieve. Secondly, I will introduce our proposed models and how it resolves some problems by design modules. And finally, I will show you the result we got and conclude the contribution of our work. Okay, so let's go to the introduction. So nowadays, autonomous driving has become a popular issue for the self-driving vehicles. In order to perceive the surroundings of vehicle and provide safety for drivers. The key to this property is 3D object detections. As you can see from the figure below, with the help of 3D object detections, it can detect objects on the road and send the information to the subsequent system for decision making. And different from 2D object detections, 3D object detection can provide more information. For instance, the depth information can help identify whether the object is too close or not. And the object orientation is capable of knowing whether the object moves in the same direction as that of the host vehicle. So besides, the speedy development of deep learning technique has led to the major improvement in 3D object detections. So nowadays, more of the intelligent vehicles are equipped with multiple sensors, such as RGB camera and LiDAR sensors. As you can see from the figure below, on the left-hand side figure is the analysis for RGB image, and the right-hand side is for LiDAR sensors. To be more specific, the RGB camera are able to not only provide rich color information and detailed contour of front views, but also are good at distantly sensing. Those properties have some benefit for the class recognitions. And on the other hand, LiDAR are especially good at capture fine-grained 3D geometries, but they provide sparse observations at long range. And those reasons motivate us to combine multiple sensors to perform accurate 3D object detections. And combine the information of two sources effectively is still challenging. As a result, there are several studies trying to address this problem. So in this research, we propose a novel two-string 3D on-road object detections, which take LiDAR point clouds and camera RGB image as input. Different from other work which transfer 3D point cloud into 2D bird eye views representations or voxelization representations, we directly perform operation on raw point cloud to preserve the informations. And in our design model architectures, a novel fusion methods let's associate information of one string with others. And the certain modules deal with the problem of different sets of objects. To verify our framework, we evaluate the results on large number of on-row data. So let's move on. Let's move on the methodology. So in the methodology, I will focus on the models architectures in our design. So here is our design models architectures for 3D object detections. As you can see, the input of the model are LiDAR point clouds and the RGB image. Because of different data representation between those, we use two different backbone networks to extract the informations. Then our proposed multi-scale feature aggregations is leveraged to exploit both high-level and low-level RGB features to capture objects from small size to large size. In addition, the proposed region fusion layer utilizes point-wise features from LiDAR features and multi-scale spatial features from the RGB string to generate the fully fused features. And these features will used for further 3D bus refinement. So in the following slide, I will introduce the backbone network we use, the multi-scale feature aggregation modules, and regional fusion layer we propose. So firstly, introduce the backbone network. So in the LiDAR string, we use .NET++ as the backbone network to extract the information of raw point count. The advantage of the .NET++ is that it can handle unordered issues and learn point-wise features of point count. The above figure is a model diagram of .NET++. And in the RGB string, we use richness 50 as the backbone network. Compared with some lightweight versions of richness, richness 50 can obtain more representative features of image, and the increase in inference time is acceptable. In addition, we use certain feature map in richness 50 to build the feature pyramid network. These multi-scale features help us to deal with different sizes of foreground objects. And at the end of the backbone network, we apply region proposal network for both LiDAR string and RGB string to generate 3D proposals and 2D proposals. In the LiDAR string, we are able to project 3D proposal with calibration informations and then generate the project 2D proposals. And on the other hand, in the RGB string, inspired by the previous work, Fuston .NET research, 2D proposals can be linked to Fuston representations. As a result, those operations will generate many pair 2D and 3D proposals for further use. And in the multi-scale feature aggregations, since there are a variety of size of unrolled objects in the real world, single-scale features lack the ability to infer all of them. So we propose this module to deal with the different size problems. And And finally, this module will generate the multi-scale spatial features, and this feature will use for the further regional fusion layer. And the next proposed module, regional fusion layers, take two inputs which are from multi-scale multi-scale feature aggregation modules and LiDAR string. This layer leverages spatial information from the RGB string and point-wise information from LiDAR string to conduct the data fusion between two sources. And at the end of this layer, we increase the information richness of LiDAR features for the further box refinement. So let's go to the experiment. And in the experiments, we validate our proposed 3D object detector in the test of 3D object detections in KITTI vision benchmark. And this benchmark provides RGB image, LiDAR point clouds, as well as the calibration file. Besides, the category of car has the most sufficient training sample in the dataset. As a consequence, we choose the category of car to evaluate the testing set performance of our approaches as other methods did before. So follow the KITTI settings. It use average precisions to evaluate, and there are three typical levels: easy, moderate, and hard, which decide occlusion level, truncate level, and distance of the object. And compared with other methods, we observe that our proposed method has great performance on hard levels. The situation represents that we utilize the raw point cloud information as input, can preserve the 3D geometry information, and propose modules to enrich the point clouds information. So that model can generate accurate bounding box in occlusions or truncation situations. We also do the ablation study to validate the effectiveness of each modules and conduct on the validation sets in the class of car. So in the first row, simply utilize the LiDAR data to perform 3D object detections without any RGB image. This is no fusion between input sources. Most importantly, if we enable the model to generate 2D and 3D proposal simultaneously and project proposal from one string on the other string, as shown in the fourth row, model can handle conditions like occlusions or truncations. So here is the qualitative results on KITTI dataset. Finally, the conclusions. So in this paper, we propose a novel two-string deep learning architectures for object detections that simultaneously conduct on both point clouds and RGB in a fusion way. In our model architectures, there are two major components. One is the multi-scale feature aggregation modules, and the other is the regional fusion layers. And these modules solve some problems I mentioned before. As a result, we are able to combine the information of two sensors with these two modules. And in the experiments, our method has a great performance under hard level. And in the future work, we think that data augmentation techniques for both point clouds and image can be developed to improve the performance. So this is this is the end of my presentations.